Hello, everyone. Welcome to this session number 6 on the practical introduction to quantum computing. As you know, we are now approaching the end of the course. Next week, we will have the last session. But the quantum initiative, the quantum technology initiative here at CERN is already thinking of preparing new lectures on quantum computing and related topics. So in order to do this in the best possible way, we would like to ask you for feedback on these initial lectures, okay? So we have prepared a small survey, and we would like to hear your opinions on what you did like about the course, what you didn't like, what are your interests regarding quantum technologies or computation in general. And this will help us in first evaluating the course. We are writing a detailed report on this first experience, and also in designing new material and new lectures for you, okay? So that will be very helpful to us. And you can access this survey very easily. Let me show you where it is. It is associated to the 7th lecture, okay? So here you see that we have a link to fill the survey, but we have also included links with feedback survey in all the other pages of the lectures of the rest of the course, okay? So if you go back here, you don't need to register or to provide any email address or nothing like that. It's completely anonymous and public. And as you can see, it's not very long. I reckon that it will take you at most 10 minutes to fill in or something like that, but it will be really, really helpful to us. So I thank you in advance for your collaboration, and I hope that you can find some free time to give us your opinions, okay? So let me go back then to the content of the course. And I would like to start by, let me also bring the chat here in case there are questions. And I will like to start by addressing some questions that you asked last week and that I told you that I will be looking into. So the first one was about the output of Shor's algorithm in Aqua's implementation. And in the documentation, there is no information about all these values that are returned with the result. But I checked the actual source code of the implementation, and it was as I was suspecting. You have this information about the number of times that the circuit has been run, and then information of how many of these runs have led to a correct identification of the factors of the number, okay? So you can use that as a way of estimating how probable is to obtain the factorization of the number by running the circuit. The other question was about the quantum effects on D-Waves computers, on quantum annealing, and whether this was something that could give you some advantage over classical computation. So as I told you, there is some controversy about this. It is more or less clear that there are quantum effects taking part into these computations and the quantum annealers, but it's not clear whether this will lead to speed up over what we can obtain with classical algorithms. So I have linked 2 papers on the page for lecture number 5, one in which researchers from Google study the behavior of these quantum annealers and show that there are certainly some quantum tunneling, quantum entanglement going on with these computers. But there is also another paper that puts this into context and compares these effects to what you can obtain with classical algorithms. So if you are interested in the topic, I think they are 2 quite readable papers, and you can find more information about this controversy there, okay? So now let me go back to the slides, and today we are going to talk about some more algorithms for optimization, and then we are going to be talking about quantum machine learning. Okay, so let me connect what we are starting with in this lecture to what we did at the end of the previous lecture. So if you remember, we were using quantum annealers, a form of quantum adiabatic computation, to solve certain kinds of optimization, combinatorial optimization problems, okay? And for that, we need a special kind of computer, which is able to implement the action of a certain Hamiltonian that is changing with time, okay? So a natural question is whether we can do something similar, but with our regular gate-based computers, quantum computers, whether we can do this with circuits, with the computers, for instance, in the IBM quantum experience. And the answer is that yes, we can do that. There is this algorithm, which is called the quantum approximate optimization algorithm, or QAOA, which was proposed back in 2014, which can solve optimization problems of the forms shown here on the slide. So this may seem a little bit strange, but the idea here is that we have some Boolean functions, so functions of a binary string that return either 0 or 1, and some real coefficients, and then we sum up all these values, and we want to make this the minimum possible. Examples of these kind of problems are, for instance, the ones given by the max cut problem that we were studying last week. For instance, if we set this function here, this Boolean function, to be the XOR of vertices in a graph where there is a connection between those vertices, then if we assign the same value to both of the vertices, then this XOR will be evaluated to 0. But if we assign a different value to each of them, which corresponds to having them in different groups, then this value will be 1. Okay, so again, it's the same thing that we wanted to optimize in the case of quantum annealing, and there are other different problems, for instance, the maximum satisfiability problem or the weighted maximum satisfiability problem, that we can express in this way. So this way may seem a little bit complicated, but you can think for concreteness just in the max cut problem, for instance, okay? So the idea again is, well, we want to transform this combinatorial optimization problem into something that we can solve with a quantum computer. And the way of doing that is, as we did last week, to transform the cost function of these problems into a Hamiltonian. And this is something that you can always do when you are dealing with Boolean functions. It is quite easy to see that given a Boolean function, you can obtain a Hamiltonian, which is a combination of set operations like this one here, like a polynomial in set operations, which has as values, when we evaluate the energy, exactly the values that we obtained from the Boolean function. This is similar to what we did last week to transform the max cut problem from the combinatorial optimization formulation into a Hamiltonian in order to minimize the energy of a Hamiltonian. And here you can see some of the transformations that you can use to go from Boolean functions to Hamiltonians. If you want more information, you can check this paper. It's quite easy to read, and the transformations are more or less mechanical, okay? So the idea is that we have something like this, something that we evaluate on binary strings and gives us a number. We want to minimize that, and we can transform that into a Hamiltonian, which has energies that corresponds to the different values that we obtain when we evaluate this with a binary string. Okay, so this is similar to what we did with quantum adiabatic computation. Then what we do is to think of the process that we used in quantum adiabatic computation, in which we had a Hamiltonian that was evolving over time until it was transformed completely into a Hamiltonian whose ground state was a solution to our problem, okay? And this is something that we can do with, for instance, D-Waves quantum computers, because they are built to implement this interaction of a Hamiltonian that is changing over time. But this is something that we cannot do directly with a quantum computer based on quantum circuits. But remember that when we have a Hamiltonian, the evolution of the system is given by Schrödinger's equation. So we can try to solve Schrödinger's equation, and then what we have is a unitary transformation that governs the evolution of the state that we have in the system. But we know that any unitary transformation can be expressed or approximated, we talked about this several lectures back, by means of using quantum gates. So that is what we are going to do. We are going to use something that is called sometimes trotterization of the action of a Hamiltonian. And without going much into the details, you obtain something like this. It's like you integrate this Hamiltonian, this action of the Hamiltonian, in small pieces, and you obtain transformations which are kind of rotations, related to rotations, as we will see in a minute, which have parts which act like the final Hamiltonian and parts that act like the initial Hamiltonian. And it can be proved that in the limit, if we take a lot of these interactions, a lot of these small unitary transformations, we get something that very well approximates the evolution of the system. So the idea is that, well, you see here that we have some angles, these betas and gammas, that somehow are parameters of this evolution. The idea of the QAOE algorithm is to fix one value of P, which won't give us the correct complete evolution of the system or the complete solution to Schrödinger's equation, but will give us an approximation even that can be good even for low values of P. And then try to optimize to obtain the best parameters of these values of beta and gamma angles, okay? Starting with some state that is easy to prepare and that we can evolve with this parameterized transformation in order to obtain something that is an approximation of the solution to our problem. And this gives rise to this QAOE algorithm, which is again a hybrid method like Shor's algorithm. We are going to use a classical computer and a quantum computer for some of the steps. And this is something that we will see in other algorithms that we are going to study today. And this is something that I think it's going to be the norm for the use of quantum computation in the near and medium term, at least. I don't think, and people in general agree, that quantum computers are not going to replace completely classical computation, but it is very likely that they will be used as kind of quantum accelerators in the same way that we have, for instance, GPUs or TPUs or other hardware accelerators that we can use to solve specific problems for which this kind of hardware is especially good. Quantum computers can be used to accelerate certain computations that are difficult for classical computers, but because of the nature of quantum computing, it's easy to solve with this kind of devices, okay? So this is something that we will see in other algorithms, and that I think it will be very, very likely the future of quantum computing in general, okay? So what is the idea of the algorithm? Remember that we have this expression here that depends on some parameters, and we hypothesize that the solution to our problem can be expressed as this state for some values of the parameters, okay? So we want to obtain the best parameters, the ones that give us the lowest energy with respect to the Hamiltonian that is encoding our problem. So the idea is to fix first one value, the value of P, to know how many terms we need to use in this parameterized state, and then choose for instance, at random, some values of the angles beta, beta and gamma, and prepare the state with those values. So prepare the state, this state in the quantum computer with those values. Then we estimate the energy of that state for those values, and then we try to vary the values of the parameters in order to reduce the energy of the state that we are preparing. Okay, and we repeat this a number of times. For instance, until the difference in energies between one state and the next is less than some threshold, or when we have run the algorithm for a number of steps or whatever. Okay, it depends on the kind of strategy that we are using to minimize this energy. And then we measure that state, that final state, and from that we can obtain good approximate solutions to our problem. Okay, so this is the idea. And of course, some of the steps are done in the classical computer, some of the steps are done in the quantum computer. In concrete terms, the only step that we do on the quantum computer is this state preparation, because this is exactly what a quantum computer is able to do. It's able to prepare states that can have entanglement, that can have a lot of different amplitudes because of this superposition of the different states. And this is something that in general is hard for classical computers. Okay, so the idea is then, well, how do we prepare this state, which seems kind of complicated? And the thing here, the surprising thing, is that it's not that complicated, because as I was telling you before, these are very similar to rotations and to the rotations that we studied on the second lecture. And in fact, some of them are just rotations. So let me explain you just very briefly how to do this. Well, first of all, notice that we need to prepare this initial state, and then we need to apply some quantum gates in order to make this evolution. But this initial state is something that we are very familiar with. We can prepare this just with a column of Hadamard gates. It's the superposition of all the basis states, and this is something that we have been using in, I think, all the algorithms that we have studied so far. Then we have rotations or unitary operations that depend on these X operators, because we are starting with the grand state of the sum of these operators, and then our HI here is this sum of these X operators. But this is exactly the kind of rotation that we were studying when we were dealing with just one qubit, okay? And we can prepare that as a rotation around the X-axis, or we can use it, or we can simulate it also with a Z rotation, provided that we do this basis change before and after with these Hadamard gates. Okay, so this is something that we already know how to do. So the only thing that we need to learn how to prepare are these rotations or these exponentials of the Hamiltonian that represents the energies of our system, that codifies the cost function, the Boolean cost function that we are trying to minimize. But remember that we have transformed the cost function into this polynomial over sets. So this HF here is the sum of these terms that only involve set operations. And all of them commute to each other because they are diagonal in the computational basis. So we can compute this exponential of this sum as the product of the exponentials of each of the terms. Okay, this is something that is comes from results in linear algebra, and then we only need to deal with this kind of term. But this kind of term is quite easy to prepare, because we can think of this as the action that it does on the computational basis. And it's very easy to see that, well, this is the exponential of something that is diagonal. This matrix here has eigenvalues which are either 1 or -1. So the eigenvalues of this matrix, which is again going to be diagonal, are either I to the minus I gamma k or e to the I gamma k, okay? So they kind of act like rotations, because this is the action that rotation around the z axis with one qubit has, okay? So what we can do is to see that depending on the parity of the qubits that are involved in this Hamiltonian here, if the parity is even, then we are introducing this this phase, which is e to the minus I gamma k. And if the parity is odd, then we are introducing the same phase but with the opposite angle. Okay, so what we can do is to compute the parity of the qubits and then do a Z rotation, because this is the action of a Z rotation. And for instance, for a simple example like this one here, what we can do is to use CNOT gates to compute this parity, then do the rotation around the Z axis, and then restore the value of this qubit that we are using in order to compute the parity to its original value. Okay, so this is something that you don't need to know, because the implementation that we are going to use does it for us. But this is to show you that this is not very difficult or not very different from things that we have been doing. And in fact, this is the kind of proof that you can use in order to show that with CNOT gates and rotations, you can approximate as much as you want any unitary transformation that you need. Okay, so this is exactly the kind of technique that you can use to prove that fact. Okay. The other thing that we need to do, so, well, we have chosen the initial angles and the value of P, we have prepared the state, now we have to estimate the energy. So the other thing that we need to do is to estimate the energy. But to estimate the energy in this case, it's very easy, because when we measure the state that we have prepared, we are going to obtain a binary string. And this binary string can be evaluated with the cost function C, that is the target cost function of our problem, because we have chosen the Hamiltonian HF to encode the values of this cost function. Okay, so what we have here is a state which is a superposition, of course, of the basis states, of the states in the computational basis, and we know how to compute the energy of each of the states in this computational basis just by using the cost function of the problem. So then it's easy to see that because all these states in the basis are, of course, orthogonal, when you use this Hamiltonian to compute this product here, you are going to obtain convex combination of the energies of the states, and each state is going to contribute to this energy according to the probability of measuring that state from that basis state from the state that we are preparing. So what we can do is to measure this state many times, and then average according to these probabilities the energies of each of the states that we obtain. And this is the way of estimating the energy. And then we feed this value into our classical minimizer, whatever it is. And the minimizer uses that information to give a likely or hopefully better approximation of the optimal parameters for this parameterized state. Okay. So I'm going to show you in a minute how to run this on the IBM quantum experience. But before that, I think some comments are in order. First of all, we are going from a representation with a Boolean function to a representation which is a combination of like a polynomial, a sum of terms in these set operators. So the question here is whether this expansion it's going to give me too many terms. Maybe the terms that I obtain from the Boolean functions are exponential in number. So this is something that we need to take into account, because if this is the case, then we need to apply a number of gates that is exponential in order to compute the evolution under the Hamiltonian. So we need to take care about this. But in many interesting cases, for instance, in the max-cut problem, we have seen that the number of terms that we obtain in this expansion as a Hamiltonian is polynomial, okay? So provided that we can obtain something that is polynomial, this method can be efficient as long as we have a quantum computer that can prepare the states, okay? Another thing that is interesting to see is that when I make P bigger, of course, I have a parameterized state that is more powerful, is more expressive, okay? So it's more likely that I have states included in this manifold that I'm exploring with the parameterized state that are close to the values that give the minimum energy for the Hamiltonian. But even for small values of P, it has been shown that for some cases, we can obtain good approximations. So something that people are doing is to study the application of this QAOA algorithm for combinatorial problems with values of P that are not very big. For instance, P equal to 2 or P equal to up to 5 or something like that. And the results are quite interesting. It's not clear yet, again, like in the case of quantum annealing, whether we are going to obtain a real advantage over classical algorithms or not, but it's a lively field of study nowadays, and I think it's very interesting. In fact, here at CERN Open Lab, we've been working on this QAOA algorithm, its possible applications, and also the influence of the choice of the classical optimizer. I have not talked much about how to choose this classical optimizer, but it can have a great influence. We have made some studies about this. We have written a paper that is currently under review and hopefully will be published soon. So, well, this is something that I think it's an interesting field of study nowadays and can lead to some interesting applications in the future, okay? In fact, people have been using this kind of technique, this QAOA, for high-energy physics also. So I want to show you here just a quick example, what these people from the Institute for Complex Systems in Fribourg here in Switzerland and people from the Lawrence Berkeley laboratory have been doing is first to formulate the problem of particle track reconstruction when you have hits in the detectors of the accelerators, and then transforming this into a problem that can be solved first with quantum annealing, and then with QAOA. I think this is work in progress yet. There are not still results, but I think it's something that it's interesting. You can take a look at this paper. It's quite easy to read. You obtain an expression like this where these coefficients express the compatibility of triplets of hits in order to reconstruct a track of the hits of a particle, and then you can solve this either with quantum annealing or with QAOA. Okay, so this is something that is being explored also in the field of high energy physics. So let me now show you how to solve this with computers in the IBM Quantum Experience. You have these notebooks as always in the Indico page for the lecture, and I'm going to run number 11. Well, I'm not going to run it because this takes a little bit more time than the ones that we have been running in previous sessions. So I have already run it. You can run it yourself and see and check the results. But in order to speed up the process, I have already run it, and I have here the results. Okay, so again here, what I'm going to do is to use the implementation that is already provided by Qiskit in the Aqua package, and for that I need to provide the Hamiltonian to which I want to apply the QAOA algorithm. In order to do this in a way that is similar to what we did with quantum annealing, I have implemented this function here, which, given the coefficients in an Ising model, gives you back the Hamiltonian that then you can use with the QAOA. Okay, so for instance, if you have an instance of the max cut problem like this one here, you use this function and you obtain this expression here, which is of the form that I showed you on the slides. It's a polynomial on sets. And this is something that now you can feed into the QAOA in order to obtain approximations of the solution to the problem. In this case, if I remember correctly, the solution gives an energy of -3. So first, what I did was to use the QAOA algorithm with this value of P equal to 1. So this is a very crude approximation of the solution to the Schrödinger equation, because I'm only taking one term, okay, in this trotterization. But you can see that if I run this, I only need to create an instance of the QAOA algorithm with the Hamiltonian that I want to use, the value of P, and the classical optimizer that I want to use. In this case, it's Covila, which is one of the optimizers that in our studies here at CERN Open Lab, we have identified like the best in terms of efficiency and quality of the results for this kind of problem. And you see here that for an approximation with P equals to 1, we obtain energy which is not the optimal, because it should be -3, but it's close. Okay, it's close to the optimal. And in fact, since we are going to measure the state that we obtain, and the energies that we obtain are taken from the strings that we measure from this state, it is very likely that we obtain a string that has energy -3, which is the optimal. Okay. Of course, we can increase the value of P to 2, and then the execution time of the algorithm is going to grow, because now we have to prepare a more complicated state, and we have more parameters to optimize with the classical minimizer. But now you see that we obtain something that is practically the optimal solution. Okay. I have also included here something that I think it's interesting. This is something that we also did with our study here at CERN Open Lab, which is to consider not an ideal simulation, but a simulation with noise taken from a model provided by IBM in terms of the calibration of the computer. So here I have considered this IBM Q Odense device, and I have recovered the calibration of this device in order to construct a model of noise to be able to do a more realistic simulation of the behavior of the computer. This is something that you can do with any circuit that you want to run. We have not done it yet in any of the previous notebooks, but you can use this technique of simulating noise with any of the other algorithms. And sorry, I go back here to P equals to 1 to make the process a little bit faster. You can check what happens with P equals to 2. And you see here that when I run this now, because of the noise that I obtain or I have in the simulation, I'm not able to recover the best solution that we were obtaining with P equal to 1, but I obtain something that is approximately equal or close somehow to the optimal solution. Okay, so of course this is something that you need to take into account when you run on actual hardware. you are going to have noise and your solutions are going to degrade. But well, this is something that it's being studied also actively now in order to try to mitigate this influence. Okay, so I don't know if there are questions about this. Let me go back to my slides. Seems there are no questions. Okay, so once that we have studied this QAOA algorithm, one natural question is, well, here we are using just a restricted form of Hamiltonians which are only have only terms which are in which we have sets. But we can have more general Hamiltonians, and these Hamiltonians can be very interesting because they express, for instance, physical situations or come from chemical problems or from other interesting applications. So is it possible to generalize this approach of using a parameterized state to try to obtain the ground state, the state of minimum energy of a Hamiltonian? And the answer is yes. We have this very famous algorithm, which is called VQE, the variational quantum eigensolver, which has a very similar idea to the one that we used in the QAOA. In fact, in this kind of algorithm, we are given a Hamiltonian, which comes from whatever application, from physics or from chemistry or from whatever, and we want to obtain the minimum, the state of minimum energy of that Hamiltonian. Okay. So what we can do in that case is to prepare a state from some initial state that we usually choose from information that we have from the problem. And we also use a unitary transformation that depends on some parameters, okay, like in the case of the QAOA, that also uses some information from the problem. It's like an ansatz. And we can use this ansatz in order to prepare states that, because of the information we have about the problem, we think that are going to approximate well the state of minimum energy of the system. Okay, so this is what we call this parameterized unitary transformation is what we call a variational form, and this is why we call this algorithm the variational quantum eigensolver. This idea of variational forms or variational whatever comes also from this property that is called the variational principle, that tells me that when I have a Hamiltonian, we know that this matrix, the matrix of the Hamiltonian is Hermitian, and hence the eigenvalues of this matrix are all real values. And I also have a orthonormal basis of eigenvectors associated to these eigenvalues. So I can decompose any state as a linear combination of these eigenvectors, and then the energy of this state with respect to the Hamiltonian, it's going to be a convex combination of the energies of the states in this basis of eigenvectors. This is exactly the same as we had in the case of the QAOA, but in that case we knew, because the matrix was diagonal, that the eigenvectors all were from the computational basis. And here we can have a general basis of eigenvectors. They need not to be in the computational basis. Okay, so we can use this variational principle to see that this approach of trying to use a variational or a parameterized state given by this initial state and the action of the variational form, if we try to minimize the energy of that depending on the parameters, the best thing that I can get is the minimum energy of the over all the eigenvalues that I have. Okay, so this is sound. This is something that I can use to try to obtain the ground state and the ground energy of the system. Okay, so how to do that? Well, you see here that the algorithm is very similar to the one we showed for the QAOA, because we choose an initial state, we choose a variational form and some parameters for this variational form. In the case of the QAOA, the variational form is prescribed by the algorithm because of the form of the Hamiltonian, but here it can be a variational form and an initial state, which is given by some information we have on the problem. Then we prepare the state. This is the step that we perform on the quantum computer, of course, and then we estimate the energy. Here, estimating the energy is a little bit different. I will talk about this in a minute, but the idea is the same. We estimate the energy, and then we try to vary the parameters in order to minimize this energy. And then again, we stop when our classical minimizer tells us that it has found the minimum or something close to the minimum. Okay, so it's exactly the same kind of approach, but here the variational form is more general, and the Hamiltonian is more general. We don't need to have a Hamiltonian that is diagonal in the computational basis. So what's the difference here, or what new things we need to be able to do with the quantum computer in order to use this BQE algorithm? Well, the preparation of the state depends on this variational form, and this variational form is given by a circuit, so there is no problem with that. But the estimation of the energy is a little bit different, because now we need to compute the energy of a state for a general Hamiltonian. The Hamiltonian can have terms which are only depending on set operations, but it can only have terms that depend on other Pauli operations. It is a very well-known result that any Hamiltonian can be expressed as a polynomial in these Pauli operations. So we are going to have sets and x and y's and identities, okay? And this is going to be a linear combination of these products of tensor products of these Pauli operations. But now we do not have only terms which involve set. Measuring the energy of terms that involve set is very easy because of the variational principle, because in that case, since the matrix is diagonal, all the eigenvectors are the elements in the computational basis, and we can measure in the computational basis, estimate these energies and these probabilities, and recover the energy of the state. But when we have terms like this, the eigenvectors are no longer elements from the computational basis. So we need to do a change of basis in order to be able to measure the energy of the state with respect to this part of the Hamiltonian. So what we can do, for instance, in this case, which is a simple one, but involves all the different situations that we can find in this kind of estimation of the energy. What we can do first is, of course, to use linearity to separate these terms, and we only need to evaluate this part here and evaluate this part here. But this part here, we already know how to evaluate, because this is exactly what we did in the QAOA cases. It's what I was telling you, that we can estimate by measuring in the computational basis, because the eigenvalues, the eigenvectors are the terms or the states in the computational basis. In order to evaluate this, what we can observe is that we can transform an x and a y into a set which is conjugated by some matrices that we already know of and that we can use in our circuits. For instance, the Hadamard gate and the S gate. So this is a very easy exercise, but one that I encourage you to do. You can show that these equivalences hold. And then when we try to compute this energy here, we can expand this x and this y using these formulas, okay? And since the cool idea here, or the trick here, is that this is the conjugate of this part, and this is the conjugate of this part. So what we can do is to absorb all these operations into this state, all these operations, sorry, let me select it, on this other state. And what we have here is the conjugate of this state. And now we are measuring the energy of this state, of this whole state, with respect to a diagonal Hamiltonian. And then what we do is to apply, oh, I thought I had it here in a circuit. Apply these operations after we have applied our variational form, and then measure, as we always do in the computational basis, and estimate the energy of what we obtain in with respect to this Hamiltonian, which is something that we know how to do. Okay, so we are reducing the problem of estimating the energy with a Hamiltonian of this type to estimating the energy of a Hamiltonian of this type. That is something that we know how to do. As I told you before, this VQE algorithm can be used in order to obtain ground states of systems that come, for instance, from physics or from chemistry. And one of the first applications of this VQE algorithm was done in this paper in Nature in order to estimate with real quantum computers. I think they were using a 7 qubit quantum computer. This is the topology of the quantum computer, but they were not using all the qubits. You see here that for this molecule, they were using just 2 qubits, for this one just 4, and for this one 6. And they were, with the quantum computer, estimating what is called the dissociation profile of the molecule. I will show you this in a notebook in a minute, okay? But this is something that it has a lot of applications, because, well, of course, for these kind of molecules, we can do this easily with classical computers. But when the number of atoms in the system, in the molecule, grows, the number of parameters that we need to consider grows exponentially. And this is something that it's difficult to do with classical computers. And for maybe even, I don't know, 100 atoms, this is out of reach for our computational techniques, classical computational techniques nowadays. So this is something in which we think that quantum computing is going to be offering a real advantage, because it will allow us to study chemistry reactions and molecules that are out of reach now with current technologies. Okay, I will come back to this in a moment, because I will show you how to do this with a notebook. Okay, so all these techniques, something that you need to take into account is that here the variational forms and the initial states are taken from information from the domain of application. Okay, so this is something that has been studied, and there are some answers that can be used in order to approximate these ground states. So this VQE algorithm can be used for this kind of problem to estimate the ground state. But, well, you can think, I have estimated the ground state. What about states with a different energy? What if I want to obtain, for instance, the whole spectrum of energies of a system, or at least some of the first excited states? Can I also do that with the VQE? And the answer is, again, yes. We can use also VQE to obtain excited states by doing a very nice trick. I think this is very interesting, and this is something that we are going to, something similar to this, or the techniques that we are going to use with the quantum circuits to compute these energies is something that we are going to use in quantum machine learning also. But this is a very nice trick. The idea is that, well, I estimate with the VQE the ground state of the system, of the Hamiltonian, and I have some expression for it, because I know this. I have obtained these parameters for the variational form. Okay, so now I can consider a new Hamiltonian, which has one term, which is the old Hamiltonian, the original Hamiltonian, and then this strange term here. What is this strange term here? Well, this is, although it maybe doesn't seem like that to people who are not used to working with Dirac notation. This is a matrix. This is in fact a Hermitian matrix, because remember that this is a column vector and this is a row vector. And if you multiply a column vector times a row vector, you obtain a matrix, okay? And again, this is a Hermitian matrix. If you compute the conjugate transpose of this, you obtain exactly the same. So this is a bona fide Hamiltonian. And what is the energy of a state with respect to this new Hamiltonian? By linearity, we of course have this term here, which is the energy in the original Hamiltonian. And then we have this term here, which if we look at this, this is the conjugate, this part is the conjugate transpose of this part. And this is exactly the square of the absolute value of this inner product between the ground state that we have already estimated and the new state for which we are computing the energy. Okay, so we are adding up the original energy plus a term that relates the new state to the ground state that we already know. And if these two states are very, very close, this term is going to be close to, this product is going to be close to 1, and this term is going to be big. In fact, if I take this C big enough, then any state that is close to the ground state, it's going to have here a very big value, and then it's not going to be a minimum of the new Hamiltonian. So I'm excluding the states that are very similar to the ground state that I already know. Okay, so this is, I think, a very nice trick, and this is something that you can use in order to define a new Hamiltonian that excludes the energies or the ground state that you have already computed and you are not interested in getting anymore. Okay. The thing here is, well, now we have this Hamiltonian. How do we estimate the energy of this part here? This part here, we know how to estimate. How do we estimate this energy here? We need to estimate this inner product, okay? But in fact, quantum computers are, one could argue, only computing inner products. When we apply a unitary, we are transforming a state into a different state, and then we are measuring in the computational basis. But measuring in the computational basis is like doing projections over the elements in the computational basis, and that is an inner product. We are estimating what is the probability of obtaining one of the elements, one of the eigenvectors in the computational basis, and that is being given by exactly this kind of inner product. This is exactly what we obtain. So what we can do is to observe that, of course, the initial ground state that we have obtained is something that we know how to prepare, because this initial state is something that we prepare with a certain set of gates, and then we apply the unitary transformation. So this part here, the V prepares the initial state, and then we have here the unitary transformation. This prepares the whole parameterized state. So if I use this sequence of the preparation of the initial state, the variational form, and then the transpose, the conjugate transpose, the inverse of the variational form for the ground state, plus the inverse of the unitary transformation that I used to prepare the initial state, what I obtain here is exactly this state, okay? But this state, if you group all this here, gives you the conjugate transpose of the ground state, and here you have the state for which you are going to compute the inner product. So when you measure this and see how many times you obtain 0, this is exactly an estimation of this inner product here, which is what you need in order to compute this energy. Okay, so I think it's a very nice trick, and this is something that we are going to use also in the context of quantum machine learning for what we call one of the proposals of doing a quantum support vector machine. Okay. Finally, before showing you the notebook, I want to show you here an application of this technique of BQE for a high energy physics problem. I'm not even going to pretend that I understand this formulation here with the Hamiltonian. I've been told that this is a quite easy Hamiltonian, which involves interaction between matter and light. It's something that is called the Rabi Hamiltonian. I have no idea, but the thing here is that you can transform this Hamiltonian, which is from the physics domains involving annihilation operators and things like that, into a Hamiltonian that only involves qubit operations. Okay, and once that you have a Hamiltonian that only involves qubit operations here, sets and x and y's, you can use the VQE. And in fact, these researchers from Fermilab use this variational form. This is the circuit, the parameterized circuit that they chose to use for this problem, and they were able to obtain the ground state and the first excited state for this problem, and they compared the results with what you obtain exactly from solving the system with classical techniques, and what you obtain with a simulator. They were using Rigetti's computers, these quantum computers similar to the ones in the IBM Quantum Experience that I told you about last week. And as you can see here, for the ground state, the approximations were quite good. For the first excited state, these are the values with the actual quantum device. They were a little bit off, probably because, as I have told you, in order to obtain the first excited state, you need a good approximation of the ground state in order to use this trick. But anyway, they obtained results that are interesting. Okay, so this can be used not only in chemistry, but also in high energy physics. I don't know if there is any question about this. Seems not, so I'm going to show you a notebook. Let me close this one and show you number 12, which is an implementation of VQE that is again provided by Aqua. And I have used this VQE in order to compute energies, ground states of molecules in an experiment which is similar to the one that I showed you on the slides that was published in Nature. Okay, so the good thing in Aqua is that, of course, because this is a very important application of VQE, they have already provided functions that let you just define the kind of molecule that you want to study, and all the computations of the transformation of the Hamiltonian into this qubit form of the ansatz and the initial states and all that are done under the hood. You don't need to worry about that. But of course, we know what is happening. We are using this variational form, we are optimizing the parameters, and we are measuring the energy and all that, okay? So here, for instance, again, I have pre-run the notebook in order to speed up the process because it takes a little bit. And here, for instance, you can define a molecule with two hydrogen atoms, which are separated by this distance. And then you just declare the kind of variational form and initial state that you want, which is provided, for instance, with this function. And then you run the VQE algorithm. In this case, I'm running it on the state vector simulator. And what we obtain here is a lot of information about the molecule. Again, I'm not an expert in this kind of application, so I don't know what some of this information means. But for instance, here we have the ground state energy, okay, which is the kind of thing that we were explaining in the slides, okay? For comparison, I'm showing you here a solution of the same problem, but in this case with a classical eigensolver for this reduced situation in which you only have two atoms. We can do it classically, and here we obtain minus 1.1373. With the classical method, we obtain something that is almost identical, okay? And now I have repeated the same kind of experiment, but changing the distance between the atoms. This is called this is what is called a computation of the dissociation profile. What is the energy depending on the distance between the atoms, and what is the energy that I need to do to apport to the energy to the system in order to separate the molecule. And I have done this with both the VQE in the quantum simulator and with the classical method. And I have plotted here the results. And you only see one line because, well, the exact solver should be in blue and the VQE is this orange, but they almost coincide, okay? So, of course, this is with a quantum simulator with no noise, but this is very promising. This is something that we can hope to use in the future when we have somewhat bigger quantum computers in order to solve this kind of problem. Okay, I think it's a very cool application and a very interesting example. Okay, so let me go back to my slides. Questions up to this point? Okay, so let's move then to the quantum machine learning part, which, as you will see, also uses this idea of variational forms and of computation of inner products. So these ideas that we have been studying in the first part of the lecture are going to be useful also for the examples of quantum machine learning that we are going to study in this part. Of course, quantum machine learning is the combination of quantum computing with machine learning, but depending on who you ask, this can be or can mean different things, okay? So to explain the kind of examples taken from quantum machine learning that I'm going to be focusing on, I have taken this, this image from a book, a very interesting book, which is listed in the recommended resources by Schuld and Petruccione, in which they classify the combinations of classical, of machine learning and quantum computing depending on whether you use classical or quantum data and whether you use computation done with quantum computers or computation done with classical computers, okay? So we have two axes here, depending on the processing device, whether it is classical or quantum, or depending on the data generating system, the input data, whether it is classical or quantum. And we have several different combinations. To us, the most interesting one, or the one I'm going to focus in for reasons that I will explain later, is the combination of classical data with quantum computers. This, of course, is the kind of combination of machine learning and quantum computing that we can do more easily nowadays with the kind of computers that we have, because, of course, we could also use quantum data. And for instance, the Quantum Technology Initiative here at CERN, it's exploring the possibility of quantum sensing, for instance, to use quantum data or to obtain quantum data in quantum states from experiments. But nowadays, it's difficult to do that, of course. And we could also use quantum data and analyze it with classical machine learning. But then it's not so interesting to us because we are interested in using quantum computers. Okay, so we are going to focus on this quantum computing used on classical data and inspired somehow by them, by the developments in classical machine learning. Okay, so there are two ways also of approaching this combination of processing classical data with quantum algorithms. The first one is to try to take parts of the algorithms that we use in classical machine learning and accelerate them with quantum computers. This is something similar to the kind of algorithm that we have been studying in the first part of this lecture, in which we use the quantum computer as an accelerator for certain parts of the computation, not for all the parts, but only for certain parts. And this is something that you can do because in many of these classical machine learning algorithms, you need to use, for instance, methods to obtain solutions of linear systems of equations. And this is something that we have already mentioned. We have not studied this in detail, but we have already mentioned that we can do with an algorithm which is called HHL, which is based on the quantum Fourier transform and the method of quantum phase estimation. So with this kind of techniques, you can define what is sometimes called the quantum basic linear algebra subroutines, or QBLAS, which can help you in accelerating under certain conditions the operation of classical machine learning. Okay. However, there are some problems with this. There are some limitations on how we can use this kind of approach. For instance, it's not very clear how to load the input to the algorithms. We also have the problem of reading the output, and we also have the problem that usually, although the number of gates that we need for these algorithms is polynomial, it is still way out of reach for the kind of quantum computers that we have now. And we also have, of course, the problem of noise and decoherence and all that, okay? So to solve some of these problems, for instance, the problem of loading the data on the computer, some authors have explored and have proposed this idea of a quantum RAM that allows you to query information and to load information and to obtain information, the classical information that you are going to use, in superposition. And this is something that could help in mitigating these kind of problems that I was mentioning. Okay, but this is still under development in different theoretical research, and it's not something that we can use right now. Okay, and you can study a lot of approaches like this one of accelerating classical methods for machine learning, like, for instance, I don't know, Boltzmann machines, support vector machines, reinforcement learning, perceptrons, PCAs, a lot of things that you can do taking parts of these algorithms and accelerating them with quantum techniques, and you obtain provable speed ups under certain conditions. But you see here this mark that shows that, well, there are some limitations on the applications of these techniques. Okay, nice, interesting paper that talks more about this approach is this one, also published in Nature, from which I have taken this table. And if you want to explore that, I encourage you to read the paper. It's quite easy to read, but I'm not going to focus on this kind of approach because this is not something that we can use now in the near term. And there are other interesting proposals in the quantum machine learning field that we can explore now, we can use now with the kind of computers that we have. And in fact, as I will show you, are already being explored in the field of high energy physics. So I think it's more interesting, although the other part is also fascinating, and the theory is very rich and deep, but it's not so practical in the short term. Okay, so what is the kind of thing that we can do, and why does it depend on the kind of quantum computers that we have? Well, it has been said that the era of quantum computing, the age of quantum computing in which we are now, it's what is sometimes called the NISQ era, or NISQ age, which comes from this term, which is noisy intermediate scale quantum computers. Okay, because the devices that we have now are noisy, they are prone to errors, they suffer decoherence, they are not fault tolerant. Okay, they are also not very big. We have computers of up to 50, maybe 70 qubits. Maybe in the next year we can reach 100, something like that. Okay, but not very big. And also they are not fully connected. We have talked about this several times in the past. In order to entangle all the qubits, we can use these CNOT gates, for instance, but we cannot apply a CNOT gate from any qubit to any other qubit, at least with some of the technologies that are the most popular nowadays. Okay, so we have some limitations. We cannot easily implement these solutions with the HHL algorithm or with quantum phase estimation or the other techniques, but we have some algorithms, some computers for which these algorithms based on variational forms can be good, because, well, in variational forms, you have seen that, for instance, in QAOA, if I have some noise, I do not obtain the same quality of solution, but I obtain something that is approximated, an approximated solution that for some problems can be good. Okay, and the noise and the limitations of the computers in this kind of application are not so severe as, for instance, in HHL, where if I obtain something that is not the solution of the linear system of equations, I can have something that is not useful, for instance. Okay, so we are going to focus on the applications of quantum machine learning with these NISQ devices, with these computers that we can use nowadays. As I mentioned, there are very interesting experiments being carried out in the last few years, for instance, in the field of high energy physics. And this is something that we are working on also here at CERN Open Lab in different problems. As you will see, some of the examples that I'm going to show are work from these researchers here at CERN. So I think it's a very interesting topic. Okay, so the first thing that we are going to study are these quantum support vector machines, which are not the same. Are not the same quantum support vector machines mentioned in this table. One thing that you need to take into account in quantum machine learning is that it's a very, very young field. It has exploited in the last 3-4 years at the most. And some of the notation and terminology is still not standard. And so, there are several methods that are different but have the same name or very, very similar name. Okay, so this is not the same technique that they use here to obtain this exponential speed up. This is a different approach. Okay, so it's important to notice that. But the idea here is to try to move or to translate the idea of support vector machines, which is a technique used in classical machine learning, very popular technique used in classical machine learning, to the realm of quantum computing, in order to have some advantage to improve somehow the performance of these techniques. Okay, so just in case you don't know what support vector machines are, these are machine learning techniques used to classify data. So imagine, for instance, that you have some data which belong to a certain class. We are trying to distinguish the black examples here from the white examples here. So a thing that you can do is to try to separate them with a hyperplane. In this case, since we are in 2 dimensions, it will be just a line. And then you compute the distance from a new example to this line. You see whether it is in one part of the plane or in the other part, and then you classify it as black or as white. Okay, this is also the idea behind, for instance, the perceptron, a classical neural machine algorithm. But the idea in support vector machines is that we could use several different hyperplanes in order to separate the data. For instance, H1 would not work because it does not separate black from white, but H2 and H3 could do the work, could separate the black dots from the white dots. So which is the one that we should prefer? The idea under support vector machines is that you should prefer that one which has the widest margin between the closest example of each of the classes to the hyperplane. For instance, in this case, the black examples are too close to the hyperplane. The white example is too close to the hyperplane. If I use this other hyperplane, I have a bigger separation. Okay, so in order to compute that hyperplane, what you can do is to, well, say that you are going to assign values 1 and -1 to, for instance, the black and the white examples, and then you compute this product here of the hyperplane, of the parameters of the hyperplane that you are using for separation times one of the examples. And then this can be either positive or negative. If it is positive, you are going to classify the example as class +1. If it is negative, you are going to classify the example as class -1. Okay, so what you want is that the product of the real label of the example times this value that you have computed and you are using to classify the example as positive or negative, the product of this should be positive. If this is negative, then the class should be negative, or maybe it's better to say that if the class is negative, then your prediction should also be negative. And if the class is positive, the real class is positive, your prediction also should be positive. Okay, so this is the restriction that you want. And then under this restriction, for all the examples in the training data that you have, this value here, 1 over the absolute value, that the norm of W, the coefficients of the hyperplane, gives you the separation. Okay, so what you want to do is to do this value as big as possible, to have a separation as big as possible. So what you want is to minimize the inverse of this value here. Okay, so this is a formulation that you can use in classical machine learning in order to obtain a hyperplane that separates the examples with the widest possible margin. Okay, what is the problem? That the problem here is that you are imposing this condition for all the examples. And in this case, in which the dots can be linearly separated, you can always find this hyperplane. But in the general case, maybe you have some outliers here, some white dots in this part, some black dots that are close to the white ones, and it is not possible to obtain any hyperplane that separates completely all the black examples from the white examples. In that case, we use a formulation of the support vector machine model that is called the soft margin, in which we allow these conditions to be violated to some extent. But then this violation is something that we want to happen not very often. So we add this penalization, this regularization term here. So if we have a lot of violation of the conditions, then the total cost of the model goes up and it's not going to be selected. Okay, so this is a quite common technique in many machine learning approaches to add this kind of regularization terms to give more flexibility to the model, but without giving like complete freedom in order to violate as many conditions as possible. Okay. Now, in order to solve this kind of problem or this kind of model with this kind of optimization problem, which is a general formulation for support vector machines, what we usually do is to consider what is called the dual formulation of the support vector machines. Instead of solving this kind of problem, we solve a related one that you can obtain by using Lagrange multipliers and things like that, which has exactly the same solution, but is formulated in terms of these coefficients alpha I, which should be between 0 and this regularization term that we had added on the soft margin case, under this restriction here. And the function that we need to maximize, this is important to notice, it's given in terms of these products here, these inner products here, between the examples of the training data that we have, okay? And it can be proved that if we solve this problem, the solution of this problem gives us a solution of the original problem, of this other minimization problem, and we can recover the values W and B from the coefficients alpha I that we have obtained from solving this maximization problem. And in fact, we can use this alpha I directly in order to classify new examples. Again, by using something that takes into account the inner product of the examples and the examples in the training data and the new example that we want to classify. Okay, so this is something that we can use in order to define a generalization of the support vector machine model that instead of hyperplanes of linear separations uses more general functions or more general boundaries in order to separate data. It can be the case that you have data that you want to classify that are not linearly separable, like this case here, but you can define a different kind of function, a different kind of boundary that separates, in this case, the blue dots from the red dots. And sometimes this separation can be expressed as a linear separation, but in a bigger dimensional space. We can embed the original input space in what we call a feature space, and then the data that was not separable in the input space is linearly separable in the feature space, okay? So we map the examples, the xi's, to some vectors in a higher dimensional space with this, sorry, with this function that we call a feature map, this phi that takes the input space to a higher dimensional space, and then we solve the support vector machine problem in that higher dimensional space. And this can be seen to work well in many different situations for classical support vector machines. And the idea is that, well, we can transform the optimization problem by considering this higher dimensional space. And what we obtain in the dual formulation is a very similar problem, but now instead of having to compute the inner products of the original examples in the input space, we are computing the inner product of the transform vectors in the future space. Okay, and the rest of the formulation is exactly equal. And then to compute the level to classify a new example, again, we don't need to be able to compute this transformation explicitly. Maybe this transformation gives us something that is very high dimensional or even infinite dimensional. Sometimes it happens. But as long as we can compute these inner products from the expressions of the original points, we can solve the problem and we can classify new examples. And this function that computes this inner product in the feature dimensional space is what is called a kernel, and this is why this is called the kernel trick. Okay, so this is theory purely taken from classical machine learning, but the thing is that we can explore this idea of the kernel trick to use a feature map that is given by a variational form. Why is this interesting, or why is this can be advantageous in order to obtain something that is more efficient or offers better results than classical machine learning or classical support vector machines? Well, remember that in the Hilbert space in which we have these states of the qubits, the dimension grows exponentially with the number of qubits. So the idea here, proposed, for instance, in 2019, last week by researchers from IBM, is to embed our input data into a Hilbert space by means of one of these variational circuits. So we use the input data as parameters in the variational form, and then to compute the inner product with the quantum computer. This is something that for certain feature maps, for certain variational forms, it's not possible to do with classical computation because you are working with this exponential number of parameters, or it's supposed to be not possible to do that with classical computation. You know that we have not mathematical proofs of that kind of fact, but it's all the evidence seems to point in that direction. So it could be beneficial to study the possibility of embedding our data into this Hilbert space, manipulating the data with the quantum computer, computing this inner product, and then solving the corresponding minimization or maximization problem in dual form for the support vector machines in order to obtain the coefficients alpha I. And then when we need to classify a new example, again, we use this form here to obtain the label, and this computation here of the inner product is done again with the quantum computer. Okay, and we already know how to compute this kind of inner product. This is exactly the same kind of situation we had in the VQE model when we were trying to compute inner products of the ground state with the new states that we were probing. And in this case, it's even more simple because we don't have an initial state. The initial state is always 0, and we have this variational form that takes the input data, the original input data, into a representation as a state in the Hilbert space. And in order to compute this inner product, that is what we need to define a kernel function like this one here, is the only thing that we need is a circuit like this one here. Okay, and again, we run this circuit. The explanation is exactly the same that we had for the VQE. It's the same trick, and we use the, sorry, I went too far. So then we run this circuit in order to estimate the frequency of measuring 0, and that gives us an estimation of this value here. Okay, and then we solve the problem with classical techniques, the problem of the dual formulation of the super vector machine. We obtain the alpha i's, and when we need to classify a new example, we use this formula here, and to compute the kernel, to compute this inner product, again, we use a circuit like this one. Okay, so this is the idea of quantum support vector machines in this formulation, in this proposal from last year, from researchers working at IBM. And this is something that has already been used for high energy physics. I have taken these slides from a presentation, a seminar given by Xiaolang Wu little bit more than 1 month ago. I have linked the YouTube recording of this seminar on the Indico page, because I think it's very, very interesting. It covers different models of quantum machine learning used for problems in high energy physics. So it's closely related to our topic today. And I'm going to show you several examples of how this group of researchers led by Xiaolang Wu use these techniques for high energy physics problems. I want to mention that among the researchers involved in these experiments, we have 2 researchers from CERN Open Lab, which have been collaborating with the other teams in order to obtain these interesting results. Okay, so the idea here is, again, like something that I showed you last week, to classify a series of events in collision of particles to see whether a Higgs boson has been produced or not. And we have a signal set of events and some background, and we want to separate the signal from the background. Okay, so this is a classification problem in which we can assign, for instance, label 1 to the signal, label -1 to the background, and we can use, of course, classical machine learning techniques like the support vector machine. And if we can use the support vector machine, we can also use the quantum support vector machine. And this is what these researchers did. And I'm showing you here part of the results in the seminar, and also in the slides from the seminar, which are publicly available. I think I have not linked them, but I will include a link. There are many more results, but here I'm showing you that these results, which were run on the Amazon AWS simulator, are a little bit better in terms of classification power than, for instance, binary decision trees, or no, I think this was boosted decision trees, so classical machine learning technique, or support vector machines. It's not a big difference, but it shows that you can obtain both with they tried both with the IBM simulator and with the Amazon simulator, maybe an advantage or more discriminatory power with this kind of techniques. Of course, the kind of experiments that we can do at this moment are very limited, because we have very reduced in terms of qubits computers, and our simulation capabilities are also very limited. We cannot go farther than I don't know, 10 qubits are using here. Maybe we cannot go farther than 20. I don't know, something like that. So we expect that when we have quantum computers of bigger sizes that we can use for this kind of experiment, we could observe even better performances. Okay, I want also to mention that Amazon has recently launched this program in the AWS platform, in which you can use several different, not only simulators, but also several different actual quantum devices. They have partnered with, I think it's IonQ and Rigetti and D-Wave. Okay, so as far as I know, that is not free to use like the IBM Quantum Experience. But if you are looking for different alternatives or platforms in which you want to run your experiments, this is something that you can also consider. Okay, so this is one of the results. Another result of this kind of method of the quantum support vector machines for classification of these events is shown here in this slide, in this graph. Notice that here they were using 3,200 events for the training, which is not much, but here it's shown that even with less than that number of events, the quantum methods, the quantum SVMs, can obtain values. Well, the uncertainty here is quite big. It's difficult to say that there is a real advantage, but this is also consistent with the kind of experiment. Let me go back quite a way. With the kind of experiment that I showed you last week with these quantum annealing techniques also for classification, okay? So this is a common theme in these recent experiments. It seems that somehow the quantum versions of these classical methods, in the case of quantum annealing, we could talk about the comparisons with these neural networks and decision trees. In the case of quantum SVM, of course, we are comparing with the classical SVM and also with other classical techniques. But it seems that the quantum methods are able to learn more with less examples, okay? This is just a hypothesis. It's not proved. Much more experimentation is needed to reach some conclusion here, but it's a common theme, not only in these two works, but in others that have been published recently, okay? So, well, it's also true that these models seem to flatten out faster. They don't gain that much from new examples, but there is something here which I think it's very interesting to explore, and I'm sure it's going to be explored in further detail in the near future. Okay, so before we go into another model of quantum machine learning, I don't know if you have any question up to this point. No. Okay, so then I'm going to show you how to run this kind of support vector machines, quantum support vector machines, on the IBM quantum experience. Of course, there is an implementation of these quantum support vector machines in Qiskit, in Aqua, because in fact, this was proposed by researchers at IBM. Again, I have run this experiment ahead of time to be able to show you the results and not wait here for 10 minutes for this to finish. And I also want to mention that some of you were trying this notebook before the lecture. I published it yesterday, and some people already tried to run it. And in some installations, it can give you problems. It also happened to me in my local installation sometimes. And this is because of incompatibility between the matplot library and some version of parallel processing that is used by Qiskit. It doesn't happen all the time. It doesn't happen with all the installations. For instance, here in the IBM Quantum Experience, it runs perfectly. I have the notebook here with the results, but you can run it from scratch from the beginning and it will work. But if you find this problem, it probably has to do with the use of the matplotlib library. I had forgotten about this problem. I thank you, Bogdan Pulpescu, I think was who contacted me about this issue, and I know it's related to that. And IBM knows about this, but I think they cannot solve it because it's not related to Qiskit itself. But I will try to produce a different version of the notebook without plots, so you can also run it on your computer in your local installation with no problem. But if you cannot do that, or if you want to see the results now, you can run it on the IBM Quantum Experience and it will work. Okay. Okay. So what I'm doing here is first, well, because of this, I wanted these plots because it's more easy to understand what I'm doing with the plots. What I'm doing here is, first, I'm going to generate just an artificial set of examples in order to train the classifier. I want to separate the red dots from the blue dots. What I have done is just to sample a Gaussian distribution for the red dots, another Gaussian distribution with a different mean for the blue dots. And then what I do is to define this feature map that I'm going to use, this variational form that I'm going to use in order to translate or transform or embed the input data into this Hilbert space. Okay? And you can do this in many ways. This is another field of study that I found very interesting and is very active now, because these models are quite recent. And it's what is the question here is, what is the best way of embedding your data? Okay, I will show you in the next model, in the quantum neural networks or quantum variational classifiers, some results, some theoretical results that are being developed by some researchers in order to study these feature maps and see what is the best. But the idea here is that in order to explore or to exploit the possibilities of quantum computing, you should have some entanglement, okay? Because if you don't have entanglement, then this is something that you can easily simulate with classical computers. So that's why almost all of these feature maps have some entanglement, and there are different approaches to this. You have here phase rotations and different gates. So up to this point, this is almost an art. You need to define your feature map, trying to exploit some of these possibilities, and also to fit the best feature map to your data. Okay, but well, for instance, in this case, I'm using this one that is provided in Qiskit, in Aqua, already ready to use. And then what I do is just to declare an instance of QSVM, saying which is the feature map that I want to use. And of course, I need to pass a quantum instance that in this case, it's a state vector simulator to do this computation faster. And then I train the QSVM with the training input and the training levels. This is the part in which the input is embedded in the Hilbert space. The inner products are computed with the quantum circuits, and then these values are used for the maximization, the dual form of the SVM to obtain the coefficients. Okay, and then what I did was to produce some values, some extra values taken from the same distributions in order to test. And then I used the QSVM that I had already trained to classify. And the accuracy I obtained is not big, but it's not that bad either. I mean, this problem is very easy. It's not very difficult, but I have not been like optimizing over the variational form here, just something that I took out of the box, and I obtained an accuracy of 80%. Okay, I can also use this in more real situations. For instance, in Aqua, you have the possibility of accessing some predefined data sets that are used commonly in machine learning environments. For instance, this breast cancer data set that you see here, the orange dots against the blue dots. And again, I used a feature map. In this case, I use one which is even simpler than this, and I ran the classification problem, and I obtained 0.8. Okay, now the kind of experiment that I was telling you about that is, I think, very interesting. I try with a different feature map, and I increase the number of repetitions of this building block. This is something that is very usual in in feature maps that you have a simple building block that then you repeat several times. And what I obtained with this is slightly better accuracy in the classification. Okay, and then you can play with different feature maps and different settings, number of examples, and all that to see what you obtain. Okay, back then to the last model that I want to show you today. Oh, there were some questions here in the chat. Bogdan Vulpescu tells me that the new version of Qiskit, which is 0.23.1, solves the problem. Okay, so if you install the update with the new version, it solves the problem. And Richard Polivka, hope I'm pronouncing that right, asks, so if I get the TTEH example right, each feature is equal to 1 qubit. Yeah, I think so. I think so. He's referring, or she's referring, he is referring to this example here. I don't think that they disclose the actual feature maps that they are using, because this is still under review. But I think that is the case, that they are using they are doing some reduction of the features that are used for the classification, and then they use 1 qubit per feature. I'm not completely sure, but I think that is the case. There are other ways of embedding the data that can use the qubits in a more economic way. You can embed more information with the same number of qubits, and that is something that is interesting to study. Okay, but I think that is the case. So the question was, could we take the best quantum simulator, which is at the level of 50 qubits, and compare with a 50 feature boosted decision tree support vector machine? The classification power is not only in the amount of data, but also number of features. You are completely right. I mean, this is just a preliminary experiment, or all the experiments in this direction that I know of are very preliminary. And the one limitation is, of course, well, that even with a very powerful classical simulator of a quantum device, let's say, I don't think we can do 50 qubits that easily, but let's say 40. Even in that case, the training time it's quite long. So I don't think this has been done yet, but that is also very, very important. I mean, what Richard was saying, to compare the number of features that you need. Okay, and there is a lot of work to be done in that direction. QMware.com could be useful. I'm not aware of this, I guess, simulator, which is mentioned by Marcus Flitsch, but I can try. I can try. So yeah, there are many different simulators out there, and there is a lot of work being done in that direction, and all these kind of resources are very, very interesting. I will talk a little bit about quantum simulation next week, but there are new developments almost every week, I would say. So I don't know if there are any other questions about this. Okay. Thank you for your questions, your feedback. It's also very interesting, and this is the point of having this Zoom session, to be able to interact. And of course, for the people watching the webcast or the recordings, remember that you can send me an email, and I will try to answer the questions as best as I can. So just in the last minutes that we have for today, I want to show you a different way of tackling this problem of classification, which again uses this idea of variational forms, but tries to translate the concept of neural networks from the domain of classical machine learning into the domain of quantum machine learning. Again, there have been many different definitions of what is a quantum neural network. This is not even like standard terminology. Some people call these quantum variational classifiers or variational quantum classifiers. There are different ways of calling these approaches, and there are other things that are called quantum neural networks, which are not the type of model that we are going to study here. Again, the terminology is not very standard, okay? But I want to focus on this one because I think it's a nice translation of the idea of a neural network, a classical neural network, into the quantum domain. And the idea is, again, that, well, in a classical neural network, I have an architecture of different layers of neurons which are connected to the layers, to the next layer, and we have these parameters in the neurons that we optimize over. So we have a loss function. We show the training data to the neural network. We compute the output. With that, we see how well the network is doing with this loss function that computes compares the output of the network to the real labels of the classification. If we are talking about classifiers, if we are talking about regression to the actual value of the function or whatever, and then we use this with back propagation and all these techniques used for training deep neural networks in order to obtain better parameters. Okay, so there is a simple way of translating this into the realm of quantum computers, which is to use not one variational form, but two variational forms. In the case of support vector machines, we were using just one variational form to embed the data, what we call the feature map, to embed the data into the Hilbert space. What we are doing here is first we use a variational form to embed the data, and then we use a different variational form also with some parameters, and this is what we optimize over. Okay. So, sorry, there's a question. I recommend to have a more detailed look into the QSVM for Higgs analysis. I don't know what you mean. You mean that, Stefan, that you want me to go in more detail about this example next week, or that you want more information? Sorry, not now. Okay, okay. I can provide more information. I have linked the recording of the seminar by Shaolan Wu. You can check that. There are more details there, or you can read the original paper. No, the original paper is not about Higgs analysis. I can try to find more information about this kind of thing to see if I think there is at least a publication in a conference that I can link, and you can read more about it. If I have time, next week, I will go over this, but I'm afraid I won't have so much. Okay, it would be interesting. I would be interested in explainability of the QSVM. Richard Polivka is saying. I will explain something about the explainability, okay? And Stefan says, I had to review the ACAT 19 paper, and at the time, the QSVM didn't have an effect. Okay, yeah, well, I know that this is work in progress, and there have been some developments and some improvements, but of course this is not conclusive enough yet. Okay, but I think it's an interesting field of study. Alberto Di Meglio mentions what I was saying, that the model was largely improved since then. Yes, I have compared the results in this seminar to the ones in the original report, and the ones now are much better. Yes. The model, well, there are many more questions here. Maybe I will read it later, and and I will reply because I have 5 minutes, sorry, and I want to finish this model, okay? But I can go back to this next week and link some papers. Okay, so sorry about that. Let me go back. Then here in this model of quantum neural networks or variational quantum classifiers, we use a variational form to embed the data and then a variational form with some free parameters that we optimize over. And this is similar to what we do in the classical neural network model, because we have this possibility of this architecture here, these layers of rotations or gates of whatever kind we are using, which feed information one to the other, and then to optimize this depending on the output. Okay, so we prepare this kind of circuit. We compute some aggregated value of the measurements that we take here in order to have a level for classifying the examples. For instance, it can be the probability of obtaining 0 here or whatever. Okay, so we have this value. We obtain this by repeatedly measuring the circuit, and then we try to optimize a loss function, just as in the case of classical neural networks. Okay, so we compute, for instance, this kind of average value here as the classification level. We use that average value in the loss function compared to the actual or the real levels of the examples, and then we optimize with some technique, for instance, with a classical minimizer, to obtain the optimal values, and then we have a trained classifier that we can use to predict the level of new inputs. Okay, how can we optimize over these values of these angles theta to minimize this loss function here? We can use minimizers of any kind, but as you know, in classical machine learning, one very common technique is to use backpropagation, and for that you need to compute the gradients of these loss functions. Okay, and this is something that we can also use, and it's very interesting with quantum circuits with these variational forms. I'm not going to go into detail into this. If anybody wants information, I can point you to some papers which are quite readable and explain it very well. But the idea is that since this variational form, in fact, is a rotation of some kind, we have seen before in the QAOA model that what we were doing were basically entanglement with the C-naughts and rotations. What we have here is kind of a trigonometric function, a very generalized trigonometric function, and then the derivatives of this function, as in the case of trigonometric functions, can be expressed by the same function displays some phase. Okay, so for instance, the derivative of the sine is the cosine, but you can obtain the cosine from the sine with a phase. Okay, and this is a very rough analogy. Okay, you have to do the computations and all that, but what is going on is similar to that, and it can be shown that for certain variational forms, very general variational forms, what you can do in order to compute the gradient is just to compute the circuit, but with a displacement in these parameters. Okay, and from that you can estimate the gradient, and you can use techniques similar to the backpropagation. Okay, and this only adds 2 extra evaluations to the same circuit with these new parameters in order to obtain the gradient and to do the optimization. Okay, Something that is related to questions that are on the chat, for instance, what are the problems in machine learning, in the machine learning field, which classical computers are not able to solve on classical data, but quantum machine learning can solve efficiently? Well, we do not have the answer to that. We suspect that we are going to be able to do something better, to obtain some advantage with quantum machine learning, but this is something that we cannot prove. And as I mentioned I think it was in the first lecture, because of the reduced capability of the actual quantum computers that we have, we cannot prove experimentally yet. So this is something that is under study. I think it's, I would say, is one of the hot topics in quantum machine learning nowadays, how to design experiments that show this advantage. And for that, for instance, there are, to know more about that, there are two papers that I'm showing you here that explore this direction. For instance, this paper from last year explores what is called, what the authors called the expressibility and the entanglement capacity of different variational forms. So here I'm showing you only 8, but they explore much more in their paper, and they experimentally measure some properties of these variational forms in order to give some insight on what is going on when we embed the data in the Hilbert space, and whether this can be beneficial in order to do machine learning with these representations. But this is work under development yet, and there are no conclusions, but I think it's very, very interesting. Also, very, very recent paper, I think it was published in October or November, is this exploration of what the authors called the feature information of the models, okay? And I think they called it generalized dimension or something like that, okay? And they show that for certain cases, classical neural networks and easy quantum models, in which, for instance, there is no much entanglement, show similar properties with respect to these figures of merit, this information, this information content, so to say. And you see here that these distributions of the eigenvalues of this Fisher matrix are quite degenerate. They have one value which is the most frequent, while with this quantum neural network, which is more complex, has more gates and more entanglement, the information content is bigger. Okay, so again, this is something that is not conclusive, but points to interesting directions for future study. And if you allow me, I want to finish with just a quick review of also two works. One, again, by the group of Xiaolan Wu, in which they use variational quantum classifiers, again, for problems of Higgs classification. Again, results which are similar to the ones that I mentioned before, which are comparable to the classical models in some cases. Maybe in some cases, even with quantum hardware, you can obtain something that is very close to the quantum simulator. I think this was one of the problems in the previous results, that they were not able to obtain this kind of performance with actual hardware. Okay, and also I want to briefly mention these results by the group led by Koji Terashi at the University of Tokyo, again for classification of events in particle collisions. For instance, this is the kind of feature map and variational form that they are using. You can find more details in their paper. And I wanted to highlight that, again, we see this very interesting behavior of in the paper, there are many more results and many more graphics, but I wanted to show you again this behavior of obtaining better results, results that are better than comparable models in classical machine learning, in this case are classical neural networks, with less events, with less examples. So again, this is something that particularly for me seems very intriguing, and I think that it will be explored in the near future because this is a hot topic. I don't want to keep you much more time. I will run or I will show you the results of the notebook that I had prepared with these variational quantum classifiers at the beginning of next lecture. I want to thank you again for the attention and for the interest in the lectures. Richard is asking me about the claimed quantum supremacy by the Chinese researchers. I will tell you something about that. I have not been able to read the paper yet, but I will talk about quantum supremacy next week, so I will mention something about that. Okay. So thank you again. Please, if you have the time, fill in the survey. You can find the link in any of the pages for the lectures, and if you can spare 10 minutes, it will help us a lot in evaluating this course and in designing the new installments of the lectures from the Quantum Technology Initiative. Thank you very much. See you next week.